Welcome everyone to this video here on activities of solvents and solutes as well as gases. So the goal of activities, the motivation of an activity is basically to define something that we can use for a real system but yet has similar structure, similar equations as kind of ideal stuff. Okay, think of, say, the equation of state for real gas, right? For that, we can use the ideal gas law, PV equals nRT, and modify it with this compression factor Z, right? So PV equals Z nRT, right? Where Z is in some complicated function of temperature, pressure, and volume, and blah, 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 right? Like all the real stuff gets lumped into Z, right? But we can still use this rough form of the ideal gas law, right? And so that's kind of the motivation and goal of activities, is to still kind of use the same forms as ideal mixtures, ideal gases, ideal liquids, right? But talk a little bit more about a real system, okay? And this will be particularly important when we talk about ions and the fact that, ions don't completely dissociate, right? Often we talk about like electrolytes as 100% dissociation or like very, very low dissociation, right? KSP, you got, like 1 times 10 to minus 8 molar or something, right, of some insoluble salt, or everything breaks apart, right? And often in real solutions, that's not the case. You don't have those two extremes. Things exist in the middle. Okay. All right. So the first place we're going to start is activities of solvents. Okay. And so let's recall, right, for a real solution, right, the modification of the chemical potential based off of the addition of some sort of solute, right, that affects the vapor pressure, right, of that solvent is given by the equation presented here, right, where you have this natural log of the vapor pressure in the mixture over the vapor pressure of the pure solvent, right? Now in ideal solutions, we assume Raoult's law, so we assume that this ratio of vapor pressure is just equal to the mole fraction in the liquid phase, okay, which is an approximation. For a real solution, right, we would just write it instead of, say, a mole fraction as an activity, okay? And we just define the activity of the solvent, call it A, right, as this A, lowercase a, right? The activity, and you can think of it as the effective mole fraction, right? That you don't have this ideal mixture. Instead, things are effectively mixing in this sort of mole fraction, okay? So what that means, right, is that, again, for a real solution, you have the ratio of the pressure of the mixture over the pure solvent pressure, okay? And we call that just, and we substitute in for that, right, just the activity, okay? Which means, right, that the activity itself is just defined as the ratio of those vapor pressures, right? And then we're also going to define the activity and relate it with our ideal value, okay? So we're going to say the activity, okay, is equal to the actual mole fraction, the ideal mole fraction, sorry, times this activity coefficient, where the activity coefficient, okay, is essentially this kind of deviation from ideal, right? Just like the compression factor for gases is the deviation from ideal gases, right? This activity coefficient is how our solution deviates from the ideal case of having this mole fraction representing the ratio of the pressures, okay? And so plugging that in, right, that you get that the change in chemical potential can be related with the ideal value plus this correction, right, for real cases, right? We have this ideal case plus some real case correction, okay? That correction is related to the activity coefficient, okay? Right, which can be calculated, right, Either if you know the mole fraction and the activity, you can use, that equation, call it, say, equation 1 here, right? Or if you know the mole fraction and the vapor pressures, you can use, say, equation 2 here, right? But yeah, okay. And so that's what the activity is for a solvent, right? And again, it's just how we define it as this, and it allows us to, again, use these very same type of equations that we think of using and things like that, right? But then apply it to real systems. But then now, right, we either have to beforehand know what this activity coefficient is, or we're going to have to determine it experimentally in lab in some way, right? So for solutes, okay, right, for solute, right, those obey Henry's law, right? Solvent obeys Raoult's law, solutes obey Henry's law. So this ratio of pressures relate to the mole fraction of the solvent times the Henry's law coefficient, Kb, right? Or Henry's law constant, sorry, right, divided by P star, right? Henry's law states that XB times KB equals PB, right? That's Henry's law, right? And so just substitute that in, okay? And we're going to rewrite our ideal chemical potential, right? Related with the mole fraction, kind of like we see for the solvent. The only thing here is now we're using this mu b naught, right? This standard chemical potential, if you will, right? Which is related with the chemical potential of the pure solute plus this term here, which is just a constant, right? The vapor pressure of the pure solute is a constant. It is a value, right? And the Henry's law constant of the solute is also some constant value, okay? And so this is just some constant shift to the chemical potential, okay? So, right, and so then we define, right, so this is our ideal, right, chemical potential change, right, based off of the solute being added to the solvent, right? Then our real value is just going to, again, replace the mole fraction with the activity, okay? And again, the activity can be related with this mole fraction and the activity coefficient, and then you're left again with this ideal case, right, plus some real correction factor, okay, right? Right, and so this, right, and then talking about some limits, right, right, in dilute solutions, as the mole fraction of B goes to 0, right, the activity of B is going to approach the mole fraction, and gamma sub B is going to approach 1, right, because you're approaching Henry's law, right, you're approaching this ideal case, right, an ideal dilute solution, right. Now, often we don't use mole fraction, we might use the molality, okay, and so in this case, right, we'll often instead, right, use this as sort of the chemical potential of the solute, okay, right, where now we use B here, the molality, okay, where we're kind of this reference chemical potential, if you will, here, mu B naught prime, right, is defined for a concentration of 1 molal, okay, right, and so again, that's our real case. So our ideal case is again related to activity, and then this activity, right, is defined as the activity coefficient times the molality, right, divided by 1 molal solution, right, kind of get rid of the units here, right. This activities, right, this activity is still unitless, right, and so, right, as before, right, as the molality goes to 0, right, the activity approaches that molality, and the activity coefficient still equals 1, right. But yeah, so right, the only difference between this slide and the previous slide, right, is that essentially our our kind of reference, pure chemical potential has been modified slightly, right? That right, mu B naught prime, right, is equal to the chemical potential of a pure solute, right, plus this RT ln of KB divided by PB star, right, and then plus RT ln, or actually not plus, so it'll end up being minus RT ln of B naught, 1 mol. Which actually this term comes to 0. Oh, right, no, so there's going to be an extra term RT, then ln, and there's some things with like molecular weights and things like that. That's thrown into that correction. Okay, it's not really important what that is, right? But just it's a bunch of stuff that's lumped in, right? And why this ended up not really mattering for things that we're interested in is because, often in chemistry we're concerned about changes in things, right? How things change and such, and so often we'll be taking differences between chemical potentials and stuff, just like talking about differences in Gibbs free energy, differences in entropy, right? Changes in entropy, changes in Gibbs free energy, changes in internal energy, right? So we'll talk about changes in chemical potentials, right? And this standard chemical potential is always the same thing, and so when you do changes, those cancel, and life becomes a lot simpler, right? And so yeah. Okay. All right, and the final thing to talk about, okay, is gases. For gases, the activity is called the fugacity. Okay, I'm not making that up, right? That is what it's defined as. It's called, right? So instead of activity, we talk about fugacity. Okay, right? And again, for an ideal gas, its chemical potential, right, is modified in this way, right? Where it's chemical potential at 1 bar plus RT times the natural log of that pressure in bars divided by 1 bar, right? So that ln is a unitless quantity. And so for a real system, right, we just define that pressure as the fugacity, okay? All right, this pressure initially was, say, like an ideal pressure or something like that. Right now we're going to use this fugacity, okay, which the fugacity itself is defined as the ideal pressure times this fugacity coefficient, okay, which you can derive what this fugacity coefficient is, and it's done in the book, okay, reference there on page 146, right, where basically the fugacity coefficient is related with this integral here of the compression factor Z, okay? Right. And so if the compression factor Z is equal to 1, ideal gas case for all pressures, right, then that integral comes out to just be 0, and the natural log of phi equaling 0 means that phi has to equal 1, and so your fugacity equals your ideal pressure, right? So just, so just kind of, checking this equation here, right, it works out just fine for an ideal gas case, okay? And so that's the fugacity, right, and that's just what it's defined as, okay? And it's the activity for gases, okay?